guys, this is Unit 6, Lesson 4, Relationships between two numerical variables. We're going completely opposite of what we've been doing so far. We're going to talk about scatter plots, and guess what? I have a graph that's not showing up. There we go, we have it back now. Okay, so a scatter plot is a two-dimensional graph in rectangular coordinates consisting of points whose coordinates represent values of two variables under study. So this is what it looks like, okay? A type of chart, it's designed to represent relationships between variables. Dots are not connected by a line. Okay, so before we had graphs where we were connecting them by a line to make like parabolas or whatever. There's no line in this one. Points may appear to form a pattern in a specific direction or to be randomly scattered. This one is just randomly scattered. You can see there's no real line because they're kind of spread out, okay? Linear relationships in scatter plots, so they can be close enough together to look like there's a line. I know I just said there was no line, but you can draw a line if they're close together like this, and this is called the line of best fit. Okay, so they're not connected by this line. This line's not jigging and jagging all over the place to connect these dots. It's just kind of floating there. And you can see that these dots kind of follow a line, and these dots kind of follow a line, but it's not a linear relationship, okay? Because it's a linear relationship, but it's not a true line where the dots are on the line, okay? A linear relationship is created when data is generally increasing or decreasing. This is increasing, this is decreasing, okay? Points tend to appear to cluster close enough together to reasonably model a straight line. So this is kind of like looking at a cloud and deciding that it's, a frog or a person or a ship or whatever, okay? This is a cloud, and it's like, if I drew a line through the cloud, then this is a positive increasing linear relationship. And in this cloud, this is a negative decreasing linear relationship. Okay, so remember this line, this orange line, is called the line of best fit. It's a straight line that seems to follow the path of the points, and it must be straight. It cannot be curved, can't be a parabola, it can't be like exponential, okay? It has to be straight. Here's a check-in. Can a line of best fit be drawn on a scatter plot when there is a linear relationship or a non-linear relationship? So which one can have a line of best fit? It's a linear relationship only. When you have something that's super scattered like this, we can't really draw a line through it, okay? It needs to be much closer together to have a line of best fit. So let's talk about nonlinear relationships in scatter plots. So when the data are not constantly increasing or decreasing, this one's obviously increasing and this one's obviously decreasing, but it's not constant. Your line would not be straight. It has a curve. So this is considered nonlinear, okay? Although several nonlinear relationships may seem to follow a direction and are reasonably close to each other, a line of best fit cannot be drawn for any nonlinear function. Functions that are nonlinear do not reasonably model a straight line. Yes, I could draw a line, but it's not straight, okay? This would be a parabola, not straight, and this is just scattered. They're not close enough together to know where the line would fit in here. It could be here, it could be in the middle, it could be up here. That doesn't have a line, okay? Here's another check-in. A scatter plot with dots that seem to model a curved line represents what kind of relationship? So if the dots are curved, it's a non-linear relationship. Has to be a straight line to be linear. Here's question number 1. This is all you. Does the scatter plot model a linear or non-linear relationship? Speed round. This one is non-linear because you don't know where to draw the line. It could be here, could be in the middle, could be at the top. Okay, non-linear. It's all wiggly jiggly spread out. Here's question number 2. I don't know why my computer beeped. What would you change to turn this graph into a linear relationship? So how could you make this a linear relationship? Okay, this one's kind of vague. I'm not even going to ask you to do it, but basically you shove the dots together, mash them together so that they can make a line, like shove these ones closer to the middle, these ones closer to the middle, whatever, okay? Here's practice question 1 at the end of your lesson. So write this answer down so go into your class. You can put your answers in. Distinguish what, if any, type of association is represented in the scatter plot. Okay, so we have our scatter plot right here. We have a line of best fit. Is this a non-linear relationship, a positive linear relationship, a negative linear relationship, or no association is represented? Well, I can tell you right from the start, from what we've learned, that this one is not going to be an option because we always have an association. Okay, so is it linear or non-linear? Well, our line is straight, so it's linear. Now, is it positive, is it increasing, or is it negative, decreasing? It's negative. So there's your answer. Okay, here's practice question number 2. Distinguish what, if any, type of association is represented in the scatter plot. So again, we know there's an association. There's always an association. So that one's not it. Okay, so is this linear or non-linear? Okay, there's no obvious place to put a line. So this one is non-linear. So get rid of both of those, and there is your answer. Gotta slide my slides. Here's practice question number 3. We have all these data sets, and it says create a scatter plot for each of the data sets shown. Distinguish which set of data represents a non-linear relationship. Now, the easiest way to do this for me is going to be to go to GeoGebra. If you're math-minded, which I'm not, you may be able to just look at these points and tell which one is going to be linear and which one's not going to be linear. I don't trust myself enough to do that. You can also just straight up graph it yourself. You can draw a graph and plot the points 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. That one's obviously going to be a straight line. I can figure that one out. And we're looking for the one that's not linear. So data set A is going to be out for me. Okay, but I'm going to go ahead and go over to GeoGebra and show you how to do this so that you can figure out which one is non-linear. I was too lazy to write all of these down, so I'm just splitting my screen. We're going to see if this will work for me or not. We're going to try it. So let's see here if I need to change any of this jazz. We're just going to go ahead and try algebra. And we're going to go with our first point, which is going to be 0, 4. Okay. Oh, nope, it didn't like that. So let's just hit that. Did it give us our point? Yes, it did. Okay, awesome. Let's do another one. 1, 6. I'm learning this as I go because I don't want to take the time to read. So far it's a line, but I mean any 2 points will make a line, so that's not really saying much. Okay, do we still have a line? Yes, we still have a straight line. Let's go 3, 3, 10. Still have a reasonably straight line. Let's go 4, 12. Okay, that one's linear. So data set B is going to not be our answer. Chink. Okay. Let's try data set C. So we need to delete. There's probably a faster way to do this, but I'm tired and I don't want to try. Okay, let's try data set C. So first we have 0 and 1. Okay, we've got that. Then we have 3 and 3. Got that. Then we have, it's so nice that it's skipping down for me. Thank you, GeoGebra. 6 and 9. Ooh, this does not look good. Then we have 9 and 27. I'm just using my mouse wheel to scroll out. Okay, this is not a straight line. I don't even need to continue. So this one is a possibility. Let's delete. It's an exponential curve. It starts out slow and then gets steeper fast. So 10, 0. Okay. We have 11, negative 1. Okay. We have 12, negative 2. We're going to zoom in on this one so we can see what's actually going on. So far it's straight. Let's go 13, negative 3. Okay. And 14, negative 4. Okay, that one's straight. So it has to be data set C. Let me get my tools. You get to actually see my tools. You've never seen that before. Reveal. Okay, so that's our answer. It has to be C. So data set C is our answer for this one. Data set C is the correct answer. These will be shuffled. Don't just pick number 3. Okay, here's quick check question 1. I won't give you the answers to these. This is the part of the lesson you get graded on. I'm not going to cheat for you. So it says distinguish what, if any, type of association is represented in the scatter plot. We know there's always an association, so that one's gone. Figure out if it's linear or nonlinear, and then if it is linear, figure out if it's negative or positive. Here's quick check question number 2. Distinguish which scatter plot represents a negative linear relationship. Okay, remember, linear means what about the line? What does the line have to be? Okay, you can do this. I believe in you. And here's quick check question number 3. It gives you points again, data sets. You go to GeoGebra, you graph them just like we just did, and then you figure out which one is a linear relationship. Okay. Next part of the lesson, here's a check-in. What kind of relationships contain data that models straight lines? By contrast, which kind of relationships may model curved lines? So which have straight lines, which have curved lines? Straight lines are linear, chink. Curved lines are nonlinear. Okay. Let's talk about quadratic equations for a minute. They have a distinct U-shaped curve, or a parabola. They contain a maximum or minimum value, which in this one is right here. Okay, so that's the vertex. We've talked about these in the past. Here's another check-in. What kind of relationship models a U-shaped line and contains either a maximum or a minimum? That's a quadratic relationship. Let's talk about exponential relationships. They're represented by a curved line. This one goes whoop. Okay. They do not form a parabola. They slowly increase or decrease before rapidly curving away. There's no minimum or maximum values for these ones. Okay. Here is example number 1. A daycare center is preparing a schedule for the coming month. They have gathered data from their clients on the amount of time their children play with toys. The scatter plot displays the data they have gathered. Based on this data, how much time does an 8-year-old play with toys in a given day? Okay, we have age down here and how many hours the kids spend playing with toys. So if you want to determine how many hours an 8-year-old plays with toys, you can examine the scatter plot or table to find the point. So we come here to age 8, which is going to be right here, okay? And we're going to follow it up to see how many hours an 8-year-old plays with toys, and it's going to be somewhere in here. If we drew a parabola, if we drew our parabolic line, okay, it's going to be somewhere right here. So the X value represents the age of the child, and the Y value represents the number of hours spent playing with toys. Using this information, you can conclude that an 8-year-old plays with toys. They're saying for 7 hours a day. Oh, this is 8. I'm sorry, I can't read. It's too small. This is our tot right here. Forgive me and my old lady eyes. Here is question number 1. This one is all you. Which coordinate pair correctly represents the given point, which is this one right here, which represents $50, which is funny because this says years and this says, oh, okay, here's $50. So if we follow this across, this represents $50. So which coordinate pair correctly represents this given point? Pause it, figure it out, come back. Okay, this is our y-axis, so we know that 50 has to be in the y-axis, so this, the y spot, xy, so this one's gone, it has to be one of these two. If we follow this straight down, we see it's between 8 and 10, so our x-axis is going to be 9. Okay, I hope that made sense to you. Question number 2, in the exponential relationship, approximately how much would you expect a 7-year-old card to be worth? This is years, this is dollars. Pause it, figure it out. So this is about where a 7-year-old card's going to be. We're going to come here. If we follow it back, it's going to be like right there on the chart. So they said about $25. I would have said 20 because it's a little low, but you know, whatever. Potato, potato. Here's practice question number 4. 2 balls are thrown from the top of a 35-foot tall building. Approximately how many seconds did it take the balls to hit the ground? Round to the nearest whole number. Pause it, figure it out, come back. Here we have height. Here we have seconds. Okay, the 2 balls got thrown, and they want to know approximately how long it took them to reach the ground. Well, they reached here between 4 and 5, and they want us to round to the nearest whole number. So we're going to say it took approximately 5 seconds because this one was like 4.5 and this is like 4 3/4 or something. Okay, so they would both get rounded up to 5 seconds. Practice question number 5. A soccer player is practicing kicking the ball. The coach captures one data point for each time she kicks the ball, noting the height of the ball at some time after it was kicked. The scatter plot shows the data points from 17 trials. Using the data, estimate the amount of time it takes for the soccer ball to return to the ground after it is kicked. Answer with a whole number. Pause it, figure it out, come back. Okay, so we want to know when it's going to come back to the ground. So we're coming clear over here, and we can see one hit at about 7.5 and the other hit about 8. They want us to answer with the whole number, so both of these are going to get rounded up to 8 seconds. Here's quick check question number 4. What conclusion is plausible from analyzing the scatter plot? Okay, this is back to the kids where their age and the hours they spend playing with toys. You have to figure out which one of these is accurate. So the age group that spends the most amount of time playing with toys is the 4 to 6-year-olds. So they're saying between here and here is the people that play with toys the most. The age group that spends the most amount of time playing with toys is 14 to 16. So they're saying between here and here are the people that play with toys the most. The age group that spends the most amount of time playing with toys is the 2 to 4-year-olds. So they're saying this age group right here are the ones that play with toys the most. And the age group that spends the most amount of time playing with toys is the 8 to 10-year-olds. So they're saying this group right here are the ones that play the most. Sorry for all the typos. Quick check question number 5. Which of the following scatter plots models an exponential relationship? You should be able to do this. I believe in you. Whales are fun. They really are. They make me happy.